All right, IBAISL2. We are finally moving away from statistics, and we are going to go back to a little bit of geometry, I guess I would call it, but it's really more like trigonometry is what we're going to get into. So, some things that you should know from before. The book assumes that you guys know the Pythagorean Theorem, which is mainly about right triangles. So, if you look at a right triangle, it should have a right angle in it. And the sides next to the angle are called A and B, and then the hypotenuse is called C if you're using the Pythagorean theorem. So the Pythagorean theorem is that the sum of the squares of the two shorter sides in a right triangle is equal to the sum of the square of the hypotenuse, or the third side. So I'm not going to do any examples with the Pythagorean theorem. I'm assuming that you guys have done that one a lot. It really doesn't come up a ton in this unit, but it is something that they said, kids should know this already. The other thing that might come in handy during parts of this lesson is good old Socatoa. So, Socatoa is not just a fun word to say. It's a reminder about three different ratios or proportions, trigonometric ratios. If you have a right triangle, which, way to go, Jelly, you did not put a right angle in there. There it is, boom. Right angle, you can find sine and cosine and tangent of certain angles in this triangle. So if you have an angle theta right here, directly across from that theta, or directly opposite that theta, is something we call the opposite side. And then right next to it, but not the hypotenuse, is the adjacent side. And of course, the hypotenuse is always the longest side. If you ever can't find the hypotenuse, you can draw a line directly across from the right angle, and it will always point at the hypotenuse. So sine is opposite over hypotenuse, sine of theta, sine of the angle theta. Cosine of the angle theta is the adjacent over the hypotenuse. And tangent is the opposite over the adjacent. So that's where the Socatoa comes from, that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. But enough about right triangles. We are going to mainly do non-right triangles. So today we are going to use one major tool, and it's called the law of sines. I'm going to show you guys where kind of law of sines came from, because if you ever forget law of sines, it's actually not too bad to kind of discover it. So if you take a non-right triangle, first of all, with a non-right triangle, the sides directly across from each side are the small, okay, start back, Jolly. The vertices, the angles, are capital letters. Always with triangles. So this is angle A, angle B, and angle C. Please notice that I'm doing kind of a fancy C with a little hat on it. That's because we are going to use lowercase c here in a minute, and lowercase c I want to easily differentiate from. So directly across from angle A is lowercase a. Directly across from angle B is lowercase b, and directly across from angle C is lowercase c. Notice that there's a relationship between the angles and the side that they point at. A is directly across from little a, B is directly across from little b, and capital C is directly across from little c. So, to discover the law of sines, we are actually going to turn this into two right triangles. So if I chop it right down the middle, I realize that this is the height of the triangle, but in purpose of not confusing h with hypotenuse and height, I'm just going to call this x right here. Now, if I use Socatoa with this right triangle on the right, so if I just look at this right triangle, this angle A, this would be the opposite side, and then B would be the hypotenuse. So from Socatoa, sine of capital A is equal to x over little b. Now, very similarly, I could look at this right triangle on the right. So I could look at this one right here. and I could say that x is the opposite side from b, and then a is the hypotenuse. So another thing I can say is that sine of b is equal to opposite over hypotenuse, which is x over a. Now, if I just focus on the algebra here, this x and this x are the same x. So I'm going to get those x's by themselves. I'm going to multiply both sides by b with the first one. So I get b sine a is equal to x. And then with the second equation, I will multiply by a to cancel out the fraction. So we get a sine b is equal to x. Now, if these are both equal to x, that means they must be equal to each other. So b sine a is equal to a sine b. Then if I divide both sides by b and a, we get this relationship. Sine of capital A over lowercase a is equal to sine of capital B over lowercase b. This is essentially the law of sines. Now, if I go back to this triangle, I, cut it in half into two right triangles by splitting it like right at C, but there's other ways to split this triangle. Like I could have split it, this is gonna be hard to see, but I could have split it like here and made two right triangles and done the same thing, or I could have split it this way and then made two right triangles that way. So in summation, there's going to be all these relationships of angles, sines of angles over their opposite sides. So the law of sines. What does the book call it? Sometimes they're British. Oh yeah, they're called. This is called the sine rule. Yeah, the law of sines, or the sine rule, is sine of capital A over lowercase a is equal to sine of capital B over lowercase b, which we discovered from our algebra, but this is also true that it is equal to sine of capital C over lowercase c. The book also wants you to know that you could flip this upside down and it's the same relationship, so you can do A sine capital A is equal to B sine capital B is equal to lowercase c sine capital C. Notice for my capital C's, I'm still doing that little fancy hat, so I can differentiate between a lowercase and a capital. Okay, the general gist with all these problems is that they sometimes will not give you a picture. They'll just describe a triangle and then ask you to find certain parts of it. So this says in triangle QRS. So this means complete triangle QRS. Excuse me? Hold on. Oh, sorry. I missed a part. In triangle QRS, let me fix these notes. QR is 15 meters. SR equals 6.5 meters. And then they use this notation of like a little hat over a S. This just means angle S. So they give us an angle, they give us two sides, and then we have to find another side. I think we should make this into a picture. I think with all these problems, you need to start by drawing a picture. The first thing I know about my picture is that angle S is bigger than 90. So I'm going to draw a triangle, but I'm going to make maybe the top angle, and you can orient this any way you want, but I'll make the top angle like bigger than 90. So this angle here, I'm going to say this is 125 degrees. That was angle S, so I'm going to put S here at the top. Now, for sides Q and R, it doesn't really matter where you put them. I'll put Q on this side. You could flop these. Whoa, calm down, Notability. Bring it back. There we are. Yeah, I'll put Q on that side, and maybe R over here. So then it says QR is 15. So between Q and R, I'll put a 15 right here. And then it says SR is 6.5. So SR is 6.5. And we are going to find angle Q. So, you guys, the big deal about law of sines and cosines, just law of sines, I always look for a pair of angle and opposite side where you know both numbers for both of them. So when I look at this, I see we have a 125 here and a 15 here, and these are opposite from each other. This is your big clue that law of sines can be used in this case. Now, angle Q is over on this side, and we don't know what this angle is, but we know that it is connected to the 6.5, that that's its opposite side. So we'll say sine of capital S, over lowercase s, which is 15, so sine of 125 over 15 is equal to sine of Q, we'll do angle Q with their little hat notation, over 6.5. Now we need to solve this. We need to get angle Q by itself. So first thing is I'm going to multiply both sides by 6.5 to get rid of the fraction on the right. So we get 6.5 times sine of 125 all over 15 is equal to sine of Q, capital Q, angle Q. Now, you guys, to get rid of a sine, you don't divide by sine, but you can actually do a sine inverse. So that's the button that's right above sine on your calculator, the sine to the -1. So sine to the -1 of 6.5 times sine of 125 all over 15 is equal to angle Q. Now, you guys, to solve this, first of all, I know that some people, like from the beginning, will take their calculator and like turn sine of 125 into a decimal or something like that. I think you guys shouldn't do this to keep your answer as accurate as possible. So I kept all the calculation in my problem because that's what I'm going to punch into my calculator. Now, before I start punching things into my calculator, you need to check that you are in degree mode right now. All the angles were given to us in degrees, so you're going to hit mode, which is up there at the top. So hit mode, and make sure that radian is not highlighted and degree is. If not, you need to highlight degree and hit enter to make sure it's highlighted. Now if I hit sine inverse 6.5 times sine of 125 divided by 15, make sure you close parentheses, use safety parentheses as much as possible, I get 20.79. Yeah, so to three significant figures, 20.8 degrees is about angle Q. And that is our final answer for the problem. Now, there's problems coming up where they're going to throw bearings at you guys. This is probably something you've probably never seen. True bearings always start from north on your compass rose and then rotate clockwise. So, just a quick picture of what a ship sailing on a bearing of 300 degrees looks like. Well, if I start with my compass rose, which is what? Never eat soggy waffles, or never eat shredded wheat, depending on how you were raised, on a bearing of 300 degrees. So, 300 degrees, you always start from north, and then you rotate clockwise. So clockwise is rotating this direction. Now, if I rotate through the compass rose, north is 0 degrees, directly east is 90 degrees, south is 180 degrees, west is 270 degrees. So 300 degrees, if I rotate, Here's 90, 180, 270, and then a little bit past 270. That would mean this is a bearing of 300 degrees because it rotates 300 degrees clockwise from north. Later on, like it'll be to your advantage to know that this is 30 degrees, like it's 30 degrees past 270. But that'll come up like in the workings of problems. But if they're saying like, if you hear on the radio a ship is sailing on a bearing of 300 degrees, that means that they're going like kind of northwest, a little more west than northwest. So yeah, you know which direction that is. So an example with this, a ship S is on a bearing of 120 degrees from port A and 42 degrees from port B. A and B are 15.2 miles apart. Find the distance between a ship and each port. So if we think of these ports basically on a straight line, where this is north, here's port A, and then the ship is 120 degrees from port A. So if you think of like a little compass rose right here, 320 degrees is going to be rotating 30 degrees past 90. So that means it's somewhere out here. So wait, say the ship is right here, and that this was 120 degrees. Now they also say that the port B is 40 on a bearing of 42 degrees. So we'll call this port B, and then that means that this, the angle between them is 42 degrees. What else did we learn from the problem? A and B are 15.2 miles apart. So 15.2 is this side right here. Find the distance between the ship and each port. Well, the first thing I'm going to do is add some extra angles in here because I know that this 120 degrees, that the other side of it will be what adds up to 180. So this side has to be 60 degrees. Another thing I should have mentioned in the beginning of all of this is that we know that all three angles in a triangle have to add up to 180 degrees. So if you add 60 and 42, that's 102, which means that this last side is, 78 degrees? Now, with law of sines, I'm always searching to see if I have that pair of angle and opposite side. Notice, now that I have 78 degrees and I know 15.2, that's a solid pair, which means I can use law of sines. Now, let's call this side little b and this side little a, because they're directly across from capital A and capital B. To be able to solve for, let's solve for b first. So let's solve for this side. 42 and b are connected, as are 78 and 52. So we can say sine of angle, sine of 78 over 15.2 is equal to sine of 42 over b. Now, to be able to solve this, I'm going to cross multiply. So get b sine 78 is equal to 15.2 sine 42. Then to get b by itself, you have to divide by sine 78. So you get b is equal to 15.2 sine 42 all over sine 78. Now, if you crunch that out on your calculator, here, I'll do it. 15.2 times sine 42, once again, making sure your calculator's in degree mode, divide by sine 78. You're getting about 10.39, 10.4. And that is going to be, what are we in, miles? Yeah, miles. So it's 10.39 miles from port A. Now, to find the distance it is from port B, which is this distance right here, it's almost the exact same problem, but now you're going to take 60 and A, which are connected because they're opposite side and angle. So we can say sine of 60 degrees over little a is equal to, once again, the solid pair being sine of 78 over 15.2. Then you can cross multiply and divide again. So let's see, that'll be a is equal to 15.2 sine 78 all over sine 60. Then you do that in your calculator and you get 13.5. Well, I want to go 2 decimal places. 15.2 sine 78 divided by sine 60. Wait, did I do something wrong? Let's try one more time. Sine 60. Oh, I see what I did. I flipped my... I did a classic math mistake of not actually... I tried to skip a step. So when you cross multiply, the 15.2 and the 60 will be together. So that's sine 60 times the 15.2, and then you divide by sine 78. So I flopped those. Sine 60 times 15.2 divided by sine 78. There it is, 13.46. .46 miles from port B. Okay, you guys, that's all I have for you today. Good luck.